Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we're going to talk about simplifying rational expressions. Now, this is the first lesson in my unit for rational functions, which is typically taught in Algebra 2 as a longer unit, but I kind of snuck it into my pre-calculus curriculum for my students because it is something that I feel like a lot of students need a lot of practice with. They see the fraction and immediately a lot of them freeze up. So that is what I'm going to work through in this kind of chapter. And for this first lesson, we're going to work on simplifying rational expressions by factoring, as well as applying the division property, applying operations, adding, subtracting, multiplying, dividing, looking at complex fractions, as well as excluded values. So the way I kind of started the lesson is I'm going to kind of work through obviously some problems with you. There are some problems though that I kind of did with all of my classes. So those are going to be kind of pre-inputted. So basically what I did is I kind of gave these prompts to my students and I just said, go ahead and simplify them. And let's just kind of see some of the mistakes you made. And students didn't always make the same mistakes that I would typically see them do. The one mistake I would see a lot, if these were kind of isolated problems, is they would want to divide out the twos. And we realize that if you divide out the twos, that gives you an answer of 3. But if you actually just apply the operation, you're going to get 5/2. So that is not the same. Dividing out the twos or just applying the operation is not the same. However, and when we have multiplication up in the numerator, when we divide out the twos or if we apply the operations, in both examples we get 3. So therefore, we can divide out the twos here, but we can't do it over here. Now, why is that the case? Well, basically the case is because in here, the 2 and the 3 are separated by addition, where here the 2 and 3 are separated by multiplication. So we can divide out terms when we have terms separated by multiplication, but not addition and subtraction. And so I did this again and again. A lot of students, again, now I just added some x's, but again, apply the operation and you can simplify. Here you can divide out the x's because the 5 in the x and the 2 in the x are separated by multiplication. Whereas you couldn't just divide out the 2x's, okay? Because you could see the answer is obviously not 3x. But over here, now that I have everything with multiplication, I can just go ahead and divide out, and that is equal to 3x. And then I worked my way one more time into expressions because typically students recognize, okay, yeah, I understand this portion and I can make this connection. But typically if I were to give them a problem like this isolated, a lot of students would want to divide out these x plus 2's. Or they would say you can't do this one because both these quantities, have addition in them. But again, the quantities can divide out what's inside the parentheses as long as they're separated by multiplication, which we have seen in, two examples here prior. So therefore, you don't need to multiply this operation and then divide the x plus 2. Nobody wants to do that, right? So therefore, we want to divide them out. Now, the understanding of dividing them out is what we call the division property. Because another thing actually I want to get through is a lot of people, confuse this with canceling out, right? And we use this word, and actually let me kind of go back to these, of terms cancel out. Well, they don't cancel out because we got to be very important. When something divides by itself, it equals 1. So in this case, actually, when I have 2x divided by 2x, actually 1 times 3x, right? Which just equals 3x. So it's very important for you to understand there is a 1 there. We just typically don't write it, but it's very going to be helpful for you to understand that the idea they divide to 1 instead of canceling out. And again, here we have, you can't divide out these terms. You can see addition separates these quantities, so therefore we can't divide them out there. A couple just things to, remember with the division property. Obviously, you're adding your terms, combining like terms, and they can go ahead and simplify. And again, I just kind of did these operations again as far as why the 2x's can't divide out, because that 2x is actually divided into both of those terms, which actually gives you an answer of 1 plus 3/2, which is 1 over 1 plus 3/2 actually, which is actually 2 over 2, so that's equal to actually 5/2, which we already knew from the original answer, right? Which is actually just the same kind of thing as distributive property. Okay, so then I talk with students about, we want to make sure we understand the division property, but again, that when things divide out, they equal 1, right? 2x over 2x equals 1. And again, I got this answer before, right? 5/2, yes, right? So obviously you wouldn't want to use all this work. You want to, make things easy on yourself, but I want you to see that you still get the 5/2. So then the next thing we want to talk about is the excluded values. And the excluded values is really a main Algebra 2 topic. I mean, in my class, we've already talked about holes, asymptotes, and the domain of excluded of when the denominator is equal to 0, of excluding those values. So that's basically why we first learn about excluded values, is values that just make the denominator 0. So the easy thing to understand is, just set the denominator equal to 0 and go ahead and solve. We're not going to be concerned if quantities divide out. Like in this case, you can see the x plus 1s divide out. For those of us that have already covered holes and asymptotes, we recognize that that is going to create, that is a removable discontinuity. And actually, I made that wrong. That's actually -1, isn't it? So -1 is a removable discontinuity, which is a hole, whereas 4 is a non-removable discontinuity, which also creates an asymptote. But for this case, we're just going to label excluded values any number that makes a denominator equal to 0. Okay, so really we're just going to practice simplifying. The main thing that, that students have a struggle with this is factoring. You got to factor the numerator and go ahead and factor the denominator and then just apply the division property. But it's really simple for what we did. So you can see I kind of gave them 2 examples here. Here's your original problem. The main idea that I told students to do is just factor, 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 factor. And obviously with trinomials, it's going to be rather simple. They can factor the numerator, factor the denominator. We see that the x minus 1s divide out. However, that doesn't mean the excluded value divides out, because 1 still makes my original denominator 0. So I just leave out the x minus 1 over, or x minus 2 over x minus 3. And therefore, x cannot equal 3 and 1. Those are going to be my excluded values. And you can see from those factors, obviously those are going to make each of those factors equal to 0. I did want to prepare students though, like, hey, we could also do some more difficult factoring problems, right? I could raise the powers now. I mean, this is, we don't have to just do easy trinomials. I could raise the power of the trinomial, or we could do factoring by grouping. So remember when we have polynomials to higher powers, and if it's a trinomial, just factor it like it's a quadratic, but then raise the power of the factors. And if you have a grouping problem, or if you have a polynomial with 4 terms, look to grouping, look to factor by grouping. So I did that, and I noticed that the quantities x squared plus 3 are going to divide out to 1. Leave me just with x squared plus 2 divided by 2x minus 3. Now this one's interesting. I only have one discontinuity here as our excluded value, which is 3/2. And the reason being is because x squared plus 3, which is my other quantity that is in the denominator, gives me an imaginary numbers. And we're not going to exclude imaginary numbers from there. We're only going to exclude real numbers that make our denominator equal to 0. So that's something we've already covered in this class as far as in our polynomials unit. So now what I like to do is just kind of work through 4 more examples with you. These are ones that I kind of gave through my class, and therefore we can just kind of, now work through these together. So there's really nothing else I can do in the numerator here. So that's just going to be left as x plus 3. However, in the denominator, basically I see that this is a quadratic trinomial. Thinking of what 2 numbers multiply to give me 3, add to give me 4. I'm thinking x plus 3 times x plus 1. Now, or I'm sorry, x plus, 1. Now again, guys, it doesn't always work this way, but it's a good idea. If you're simplifying a rational expression, something is going to divide out, right? So when you're factoring, if you get factors, most of the time, those same factors are going to be used in the numerator, right? Because you're going to be trying to divide things out. It's obviously not a rule. It has to occur. Like this could be an x minus 3, right? And then nothing would simplify. But why would we give a problem that says simplify if nothing divides out, okay? But anyways, you can see here the x plus 3s, they go ahead and divide out. When students did this though, a lot of them just put the x plus 1 in the numerator. But no, you got to think that x plus 1 is in the denominator. It's going to stay in the denominator, right? So then what do we put in the numerator? Well, obviously, understanding the division property, x plus 3 divided by x plus 3, guys, gives us 1. So 1 is going to be in our numerator. Our excluded values, x cannot equal, is going to be -3 and -1. All right, next example, looks like we definitely have some LCD going on here. I can factor out a 4x. And that's going to leave me with a x minus 1. Here, I can factor out a 2 first. So that gives me an x squared plus 2x minus 3. Let's see, it looks like I can factor that again one more time. Let's just rewrite it here. So this becomes a 4x times x minus 1 all over a 2. Let's see, what two numbers multiply give me -3, add to give me a +2. That's going to be x plus 3 times x minus 1. Okay, again, we have our terms separated by multiplication, right? So my x minus 1s divide out. And then also notice I have a 4 and a 2, right? Well, again, since they're separated by multiplication, you know, each of their terms, then I can divide out that 4 and 2. Leave me with a 2. Like 4 over 2 just simplifies to 2, right? So that's going to leave me with a 2x over x plus 3. And again, let's just go ahead and label our excluded values here. Is going to be a -3 and a +1. Now, one mistake that students will make is they'll make the excluded value 2 because they see 2 in the denominator, or they'll say -2. But again, 2 or -2 does not make the denominator 0. The only two numbers that make the denominator 0 are -3, because that makes that quantity 0, and therefore everything is 0. And 1 makes this quantity 0. Therefore, when you multiply it by everything else, it's going to be 0. 2 is just a scalar, right? 2 is going to be a stretch or compression. And we remember that from polynomials. It's not actually going to impact our asymptotes, or, you know, anything that's going on the zeros of the graph, or at least our excluded values for right now. All right, next one, let's go ahead and simplify here. Again, I can factor out a 2. So I get an x squared minus 1. Here, I can't really factor anything out, but again, I noticed that my last term is 1. So it's either my factors, you know, I know that a trinomial, guys, is going to be a product of two factors, right? And they have to multiply to give me 2x and x. Now, the nice thing about this problem is a lot of people are like, I don't know how to factor when a is not equal to 1. Yeah, but look how easy this problem is. We know that we have to be a trinomial is going to be factored to the product of two binomials. We know we have to multiply to give us 2x squared. Now, the only two numbers that we can multiply to give us 1 are +1, and -1, -1. But since our middle terms have to combine to give us a +3x, my only options are going to be +1 and +1. So let's go ahead and do this. Hopefully you recognize that's a difference of two squares. Okay, and that's going to be over 2x plus 1 times x plus 1. You can now see the x plus 1's divide out, leave me with a final answer of 2x minus 2. Let's distribute this one. I'm perfectly fine with students if they don't distribute. 2x minus 2 and 2x plus 1. But in this case, let's go and distribute because it's not really that much work. But again, the reason why I want to distribute is, again, notice the 2's do not divide out. The x's do not divide out. And again, you could say, well, these are separated by multiplication. Yeah, but those quantities are also separated across those terms. So we can't be dividing out when you have other terms separated by that addition or subtraction. So therefore, that's going to be our final answer there. And then our excluded values is going to be -1/2 and -1. All right, last but not least here, we have this problem. So let's factor out a -x, right? Because whenever we factor, I like to have things in standard form. So I want, and also to be positive. So that's an x squared. Let's say that's going to be a -x plus 1 minus 2x. Shoot. Okay, so it's a minus 2x. Oh, I can't believe I did that. Minus 1. All right. And then over here, I'm going to rewrite this again in standard form. Actually, let's just rewrite it like this, -4 plus 1. And then I recognize I can't factor this, right? Unless I factor out again. Let's knock out this negative. So if I factor out a negative here, I'm getting x to the 4th minus 1. Now, you might not recognize, it's like, well, I don't know what else I can factor out. There's nothing else in common. But remember the difference of two squares. When you have x squared minus 1, that's x minus 1, x plus 1. This is a difference of two squares just raised to a higher power. So let's go and see what this is going to be simplified to. So therefore, let's do a -x times, this is going to be, that's not right. That should be a positive one. I knew something was going on. This is going to be an x minus 1. I'm going to write this out in factored form. Even you could write it as x minus 1 times x minus 1 squared. And then this I can write as x squared minus 1 times x squared plus 1. Now again, nothing divides out at this point, right? These are similar, but that's a squared and that's an x, so they're not exactly the same. However, what we recognize though is I can factor the x minus 1 or x squared minus 1 one more time, right? So that would be x minus 1 times x plus 1 times x squared plus 1. Now, obviously, you don't need to show as much work as I'm doing. I'm just kind of doing this, obviously, for a little bit of teaching material. A couple things we notice, though, is obviously negative divided by negative is just going to turn to a positive, right? The x minus 1 squared left divide out. We're going to be left with an x minus 1 in the numerator. So I'll just write that as a positive x, sorry. So that'd just be a positive x times x minus 1. And then in the denominator, I'm going to be left with a negative x plus 1 times an x squared plus 1. Now again, we don't need to consider the x squared plus 1 as a restricted value because again, if you were to set that equal to 0, you get negative 1 square root. That's going to be plus or minus I. So my restricted values here are only going to be from here, x cannot equal positive and negative 1. Okay? So there you go, ladies and gentlemen. That was just kind of the basics of simplifying, of having students factor and then divide out. And then we kind of went into adding and subtracting. So I went with students and said, all right, hopefully you guys remember adding and subtracting some basic fractions, from back in the day. And basically, I don't know, when you first learned how to add fractions, you remembered you had to find the common denominator. And so what I did is I just kind of went down memory lane, like how would you add and subtract fractions when they didn't have common denominators? Well, when we were first learning about denominator and multiples, what we do is we just list the multiples of each of our denominator. For instance, the multiples of 2, 2, 4, 6, 8, 10, 12. The multiples of 3, 3, 6, 9, 12, right? We just kind of listed them there. And then we just found the smallest one. You could have done 12, but we wanted to find the least common denominator. And then our goal is to obtain the common denominator, so therefore we could apply the operation addition or subtraction to the numerators. So basically we understood that 6 was the least common denominator. To get 6, I just multiplied by 3 over 3 on the left and 2 over 2. Remember, you had to do that to produce equivalent fractions, okay? And therefore, you can see that's how I got the 3 plus 2 is 5. Now, everything kind of gets thrown out the window once we include variables, because if you look at this, the multiples of 3 are simple, 3, 6, 9, 12, right? But once you start including x's, you could do 2x, 4x, 8x, you could do 2x squared, 2x cubed, 2x a fourth. There's like now infinite many. And even more importantly, they don't have anything in common, right? There's no factors that 3, 6, 9, and 12 have in common except for the number. Like they don't have any of the x's in common, right? Because these have no x's, these do. So then what can we do? How can we find the least common denominator? Well, one way, if you actually look at this, rather than listing these multiples, if you really, look at this, really the least common denominator of 6 is really just a product of the two denominators. And again, 3 and 2 do not have any factors in common, right? They have the smallest multiple they have in common is 6, but they don't have any factors in common. Factors, again, are numbers that divide into them. So they don't have any factors in common. So if you just multiply them, that will produce the least common denominator. So since 2x and 3x do not have anything in common, factors in common, I'm just going to multiply them to obtain 6x. Then I find my multipliers. That's going to produce my common denominator, which is 3 over 3 on the left side and 2x over 2x on the right side. And therefore, I can't really do anything with the numerators, right? They're not like terms, but you can apply the operation and go ahead and simplify it. And then we just kind of look at this one where it's like, all right, let's just keep on adding more x's, right? So now we're going to do some binomials, x plus 2, x plus 3. And a lot of people say, oh, but they have x's in common. Well, no, x is not a factor. Because again, if x was a factor, that means x would evenly divide into x plus 2. And sure, x divides into x, but it doesn't divide into x plus 2 evenly. If you remember long division, go ahead and try it. You're going to get a remainder. So therefore, they don't have any factors in common. So just using the same idea that we just practiced to find the LCD, we're just going to multiply them across. So x plus 2, x plus 3, we're not going to expand them. Let's just multiply them on the left, multiply on the right. And therefore, now we combine our like terms. And in this portion, I told my students to go ahead and just leave the denominator in factored form. Now, the only difference is you don't want to always get in the idea. You can do it of always just multiplying the denominators, but typically we're going to do some more advanced problems where you're not going to want to do that. That's not going to be the best way to go about that. So if we look at, a number with these fractions here, you can see that 6 and 2 have a common factor of 2, right? Because if I like break down 6 as 3 times 2, you can see that they share the 2. So now my LCD is going to be what they have in common, what factor they have in common, which in this case is a 2, times which factor they don't have in common, which in this case is 3. So 2 times 3 is 6. And you can see that obviously 6 divides into 6 and 2 divides into 6. So therefore that's why it's the LCD. You could multiply them to get a common denominator of 12, but again, as I mentioned, that's going to get more and more difficult to do once we get to more problems. The nice thing about only having a common denominator where you already have a denominator of that value is you only need to multiply the other side by 3 over 3 to go ahead and get your answer. So in this case, you can see they have the same thing. What do they have in common? They both have a factor of 2 in common and x in common. So they both share a 2 and the x, right, as factors, but they don't share a common factor of 3. So when I multiply by 3 over 3, I get 6x minus 6x, and now I can apply operations to the numerator. And then last but not least here for f, you can see that they share the quantity x plus 2 in common, right? So, here's x plus 6 times x plus 2. Here's just x plus 2. So since they share x plus 2, I'm going to include that in the LCD, multiply by the product of x plus 6. And then I multiply x plus 6 on the top and the bottom. Notice on this one, though, one really important thing that if you notice my work, I'm always using parentheses when I'm multiplying. Well, not always, but most of all. See, even like 3, I put parentheses. Most of the time, I'm always putting parentheses. 1, to remind myself that's multiplication, and then 2, to make sure that notice that this is not just a 1. This is actually a minus 1, right? So it's a negative 1, and you have to make sure you distribute that negative 1. You multiply that negative 1 to the x and to the positive 6. Because if you don't, then you're not applying distributive property, and therefore you're going to get the answer wrong. So it's really 1 minus x minus 6, and that's actually wrong. So it's negative x. And that I did the distributive property and actually did the math wrong. I'm glad I went and checked my answer. Oh, wait, no, I did it right. So, okay, I was saying that's what it's not equal to, right? So that's what most people do, is they won't distribute, and they'll just write it as, 1 minus x plus 6, and then they combine the 1 and the 6 to give you 7. But remember, as long as you distribute it, you're all right. Now, we do also do excluded values for these problems, but we'll get to that in our examples. So basically the process for adding and subtracting was to factor, simplify as necessary, obtain common denominators, and then apply the operation to the numerator, and then simplify if necessary. I think all these simple problems, there was no way to do that. But let's go ahead and look at the examples, though, and kind of see if we have some options there. All right, so for the choices I chose, we have add and subtract rational expressions and label the excluded values. So these are the two examples I kind of did in class. And in this case, you can see my denominators don't have anything in common. That's why the LCD is simply just the product of them, x times x plus 2. So I just multiplied by the other denominator, basically on the other side. Notice that I had to expand that, right, as a binomial times a binomial. And then I had to add that to 3x. So I actually expanded all that out. That gave me a negative 3x, but then you add that. And then I just combined my like terms in the numerator and went and factored out. Now, there's nothing really you can factor out here. I can't factor this numerator, so I'm just going to leave it as that. But it could be something to factor out either way. So that's always just something to check, look for. If it is factorable, then that's something you want to simplify one more time. But in this case, that wasn't the scenario. And then I just find the excluded values, which is basically the values that make my denominator equal to 0. Which is 0 and negative 1 in this case. Over here, a lot of people that, again, have trouble with this, they will go ahead and just multiply denominator times denominator because like, that's easy. I like doing that. But again, if you divide this out, what you recognize is they share the factor x minus 3. So therefore, the LCD is just going to be x minus 3 times x minus 2. So I don't need to do anything to the left side. All I need to do is multiply x minus 3 on the right-hand side, which actually makes your life a lot easier, right? So I multiply that on the right side. Make sure you keep that as a negative 4, and you distribute that. I got to check my work as well. Combine like terms, and you get a negative x plus 11. Nothing's going to divide out, and my excluded values were 3 and 2. So now let's go and work on some other examples that I did in class. So I guess I didn't give myself some work here. So hopefully I can all fit these in. All right, so the LCD in this case is going to be, they have nothing in common as far as factors go, right? They both have a 1 and an x, but they're not the same. So my LCD is going to be x plus 1, x minus 1. So therefore, to obtain that denominator, I'm just going to multiply by an x minus 1 over here and an x plus 1 over here. Okay, now you can see them going to be having the common denominator. And one thing I also want to point out too, I kind of did this. I wrote this out expanded, right? So you could do the left side, do the right side, and you can recognize once they have the common terms, like you're just combining them, right? You're just combining the numerators together under the same denominator. So I did this for instructional purposes for my students and for you, but to save myself time and space, I'm just going to multiply these and then put them under the same denominator because that's what's going to happen anyways. Just make sure you distribute here and you distribute here. So therefore, I'm going to have 3x minus 3 minus, let's see, that's going to be a 2x squared. And then again, remember, you're distributing the negative 2x plus 1, so that's going to be minus a 2x. And that's going to be all over x plus 1, x minus 1. Now you can write that. As a as x squared minus 1 if you like to, but I would tell my students, it's perfectly fine. You're just leaving it as you have it. So therefore, then I have a negative 2x squared. Let's see, plus x minus 3 all over, let's see, x plus 1 times x minus 1. Okay, so again, my excluded values is x cannot equal 1 and negative 1. I'm just going to factor out a negative and make sure that this is not factorable. 2x squared minus x plus 3. Just in case nothing would factor out, but I don't think I'm going to. I mean, it could be factorable, but I don't think anything's going to factor. I don't think any of my, that would have to be like a 3, and this would have to be a positive 1. No, that's not going to work, so it'd have to be a negative 1. 3x, and that'd be a positive x. Ooh, actually that works. X minus 1, yeah, that does work. Sweet. So you can see that becomes a 2x plus 3 times an x minus 1, right? And then you can see the x minus 1s actually would divide out. So let's actually hold those excluded values here. Okay, so going a little bit further, times x minus 1 divided by the x plus 1 times x minus 1. Those divide out, just leave me now with a negative 2x plus 3 over x plus 1, where x cannot equal plus or minus 1. Okay, so again, just want to make sure, it doesn't always happen all the time, but we just want to make sure we clarify that nothing's going to divide out. And in this case, you can see that they actually divide out to give us that factored form. So we want to make sure we leave it in always our simplified, right? Because I believe the directions were to simplify them or add and subtract rational expressions. So I didn't really clarify simplifying, but if you're dealing with a multiple choice problem, you can see how that answer would have came about. All right, in the next example, they do not have anything in common, so I'm just going to multiply them. So that's x plus 3 times x minus 2. So I'll multiply these by x minus 2, multiply these by x plus 3. All right, and that's going to give us then a 2x squared minus 4x plus a 3x squared plus 9x all over my common factor of x plus 3 times x minus 2. And then I can simplify that. I can get this to be a 5x squared and then plus 5x. That gives me an x plus 3 times an x minus 2. Now, you could write this in factored form, right? You could factor out this numerator. It really kind of depends on what your teacher, wants from you. X plus 1, nothing's going to divide out. So when terms don't divide out, I just told my students, you can just leave it in factor or expanded form. Just make sure you understand that x cannot equal negative 3 and positive 2. So it was basically, as long as they had their excluded values and there was nothing that further got divided out, then I considered it to be in simplified form. All right, for B here, the issue here is, again, we say, oh, they don't have anything in common, multiply them. But again, it's like, well, let's factor out an x here. And when we factor out an x, we get an x minus 1. So therefore, we recognize here that they already have a quantity x minus 1 in common. The only thing we need over here is just another x, right? So that's actually rather easy. I just have an x squared plus a 3x squared over an x times x minus 1. Well, that problem's not too bad, right? That just gives you a 4x squared over x times x minus 1. However, you can see that an x can be divided out. So that's going to leave you with a 4x over x minus 1. And our restricted values, though, again, just because the x got divided out doesn't mean it doesn't go away. X can still not be 0 or 1. Because in the original problem, 0 and 1 would make my denominator 0. That's why they're excluded. The next one kind of gets a little tricky sometimes with people when they don't see another fraction. So again, I just told my students, write it as a fraction, right? So it's 3x over 1. Therefore, x plus 2 and 1, they need to, the only thing in common here is going to be x plus 2. So you're going to need to multiply by an x plus 2 here. And when doing that, I get 5 minus 3x squared minus 6x all over x plus 2. Let's go ahead and rearrange that and subtract out a x or a negative. See if that's going to be factorable. 3x squared plus 6x minus 5. And basically you want to see, is it going to be factorable with a 2, right? Is there going to be something that's going to divide out? So I know this is going to be 3x here and a 5. So therefore, if I need to get a positive negative 5, I can't multiply it. So two numbers give you 5 are going to be 5 and 1. I can't multiply 3 times 5. That's going to give me a 15. So then it has to be a 5 over here. And I'm not seeing anything that's going to be factorable, especially with the 2. There's nothing that's going to divide out with the 2. So that's going to be my simplified answer. And therefore x, oops, let's write that in there. Therefore, x cannot equal negative 2. And that was my only denominator, right? That was the only value that can make my denominator equal to 0. 1 was just in the denominator in that second fraction, but it doesn't actually make it 0. So really the main case for adding and subtracting rational functions or expressions is getting the common denominator, combining the numerators under the same denominator, and then go ahead and then from there, just make sure you look to simplify if you can. All right, then we worked into multiplication and division, and this was kind of like, a little bit of the same thing that we already did. So students kind of went through this a little bit quicker. The only thing that was kind of interesting though is, a lot of students, it brought back a lot of memories for like, how do you divide fractions? And one of the main things that I saw students doing was the keep, change, flip. And I'm not sure if you guys have ever learned it that way. But when they would divide something, if I had 6 divided by 1/2, they would keep the first term, change the operation from division to multiplication, and then they would flip the divisor, the 1/2, as the reciprocal. And they got 12, which is the correct answer. But the problem was I always asked them, like, why does that work? Like, why do we do keep, change, flip? Like, are you sure that's correct? And you sure that's always going to give you the right answer? And most of the students nobody could really explain the process. They just remembered it. So, which is great. I have no problem with, using some tools to remember some certain things. But I think it's really important to look at the division in a separate way so that we understand why keep, change, flips. And so what I showed them was, well, what if we wrote the fraction like this? 1/6 divided by 1/2. Well, again, my favorite fraction that I have is 6 over 1. Because 6 over 1 is just 6. So what that means is, if I have a fraction where 1 is in the denominator, I actually don't have a fraction. So right now, I have this big fraction. I have 1/6 over 1/2. Well, if I want to reduce this just to a single fraction, I need to get this number to be 1. So what should I multiply 1/2 by? Well, I need to multiply by its reciprocal, right? Because anything multiplied by its reciprocal is 1. And again, you just can't multiply the denominator by its reciprocal. You got to multiply the denominator and the numerator to keep an equivalent fraction. And when you do that, you obviously get 1 in the denominator and you get the keep, change, flip in the numerator. And that's why that works. And that's how you can go ahead and get your correct answer. So yeah, a couple other important things about multiplication as we get to it is, one thing, when we have something like multiplying, 1/2 times 6 over 2, you can multiply straight across. Like you can actually go through the operation of 1 times 6 is 6, 2 times 1 is 2, and then simplify it out, right? So you can apply the operation and then simplify. However, if I had 6 times 1/2, which I have in this case, a lot of times it's just better to understand that 2 divides into 6 3 times, right? So you could factor the 6. A lot of times we just do this in our head. We actually don't show it like this. But we can just factor things and then divide them out. We don't need to factor them, multiply them across, and then divide things out, right? So again, since our operation now is multiplication, we can apply the division property across multiplication. So that's what's kind of really important or helpful to understand now is you can apply the operation and then simplify. But to make our life easier and to make these problems easier, we're going to want to simplify them by factoring and apply the division property across multiplication. When it comes to our division problems, we're going to want to obviously rewrite them as multiplication. So basically for multiplication, we're just going to want to simplify each expression first. So simplify them and then apply the division property, right? Because we already have everything as multiplication. So therefore, you just apply the division property where you can. So, I only went through a couple examples in the class. For instance, here you can have 4 opportunities to factor, right? So you can see I went and factored everything. And then now, I don't have anything to divide my x minus 2 by, right? But again, this x minus 2 and this x minus 2, every single quantity is separated by multiplication, right? All these parentheses, these quantities in parentheses are separated by multiplication. So I just divided the x minus 2's across that. And therefore, you could see how that worked. You can see the 2 and the 4, everything is separated by multiplication. I know inside they're separated by addition and subtraction, right? That's why you can't divide, that's why you can't divide out these x's. But the quantities, you can go and divide across multiplication because the quantities are separated by multiplication. The important thing though too is also notice all these values that could be 0 in the denominators, -4, -1, and +2. Again, remember that 4 is just a scalar, right? So that's why that doesn't get divided out. And then go and simplify and then label excluded values. And that was really about it. So let's go ahead and get some factoring practice here and, just practice more factoring problems. That's really what I told students. It's not really a pre-calculus lesson in this case, but it's great practice for you as far as factoring. Uh-oh, what was that supposed to be? I think that's supposed to be a 1. Hopefully, it has to be a 1. All right. Let's go over here. So factor this. I know it's going to be a product of 2 binomials. 2x, I'm thinking this one's going to be 2, and that's going to be x, and that's going to be a +1. So I know since my last term is positive, my middle term is positive, both factors are going to be positive. I need to get 4x plus 1x is 5x, so that one works. Denominator is nothing to factor. That's nice and easy. Here I can factor out a 2x, leave me within x minus 1. And here I can see this is a difference of 2 squares, but now I have a coefficient here, which is fine. So that's going to be a 2x minus 1 times a 2x plus 1. Sometimes it might be easier to put the quantities there. Okay, so now you can see the x minus 1's divide out, the 2x plus 1's divide out. That's just going to leave us here with a 2x times x plus 2 all over a 2x minus 1. Okay, with my restricted values of, let's see, x cannot equal 1/2 or just 1. And then if I was to set these equal to 0, that would be plus or minus 1/2. All right, so let's go ahead and work on this one. So again, we have a trinomial raised to higher terms or higher powers. So I figured I remember that correctly. So that'd be a x plus 1 times an x plus 1, x squared plus 1. It would be the factored form. Here, I'm going to want to use grouping. So I'm going to want to factor out an x squared. That's going to leave me with an x plus 1 over an x plus 1. So if you factor out the x plus 1's, I'm kind of doing factoring upwards instead of downwards, which is kind of weird. But hopefully you're familiar with what I'm doing, so therefore you can see that. All right, so let's just go and rewrite this now. So I have 6x squared over x squared plus 1 times x squared plus 1 times x plus 1 times x squared plus 1 all over 2x cubed. So now you can see that my 6 and 2, those are going to divide, right? Those simplify, 6 and 2. So 6 over 2 divides just to 3. And then I have my x squared over x. Well, that's going to go ahead and simplify just to leave me with an x. I have an x squared plus 2, and my x squared plus 2 divide out. And that's an x plus 1, and then that's an x squared. They're not the same, so they're not going to divide out. So that's going to leave me with a 3 times x plus 1 all over an x squared plus 1 times x. And my restricted values, that's going to be imaginary numbers. This would be plus or minus 1. Oops, let's just write x cannot equal. Plus or minus 1. That, when you set it equals 0, gives you, again, imaginary numbers. And then, obviously, the only value that's going to make this 0 is going to be the number 0. So, therefore, that's going to be my restricted value. Okay? And then we went and talked about division. So, division is a little bit different. But, again, the same kind of thing. You're going to want to simplify first, or look to simplify. Rewrite it as a product of its reciprocal. So, you're going to be multiplying by the reciprocal of the divisor. And then we're just going to, again, simplify using the division property. But again, now that you've written it as multiplication, you can divide across multiplication. So, basically, here you have the problem. Divide it. Rewrite it as multiplication. So you can see how my numerator went to my denominator and my denominator went to my numerator. And then you can go ahead and apply your division property here. And then just go ahead and simplify. All right. Now, as far as the excluded values go, I've seen actually a couple different people teach it a couple different ways. The way that I've learned it and I feel like best understands is, again, excluded value is anything that makes the denominator 0. That means as the problem is written as a division problem, what numbers make the denominator 0? When the problem is written as a multiplication problem, what values make the denominator 0? And then what are my final solution? What values make the denominator 0? And obviously you can see that it's just repetition here for the final example, right? But sometimes when we get to further problems, that will actually change. But for right now, the final quotient is always going to be basically the sum of those first 2 examples or those first 2 operations. But that's the way that I like to teach it, and at least I had my students go and do it, is just look for those values. All right, so the first thing we're going to do is let's just factor, 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 factor. All right, so in this case here, I have a x minus 2 times an x minus 1 all over x divided by, let's see here, that's going to be 3x. I think that's both going to be minus, right? Minus 1 and then x minus 1. And again, I'm just kind of doing a guess and check in my head. I've already covered a lot of factoring problems in my class, so I kind of expect my students at this point to be fairly comfortable. And if they're not fairly comfortable with factoring at this point in my class, then they are supposed to do all the problems that I have given them for factoring practice, because I give my students a lot of problems to practice their factoring. So that'd be an x minus 2. Okay, cool. So there's the division. And obviously, the better you get at this, I'm doing this for kind of instructional purposes. You could obviously just go ahead and skip that step and just go from factor it and then write it like this as a product of this reciprocal, right? And then let's see, minus 1. So now you can see that the x minus 1s are going to divide out. The x and the x squared divide out. Nothing with the x minus 2s, and this 3x minus 1, nothing divides out there. So therefore, we're just going to be left with here, should write an equal sign, 3x times x minus 2, quantity squared, you can write them multiplied out if you want to, all over 3x minus 1. Okay. Now our excluded values are going to be x cannot equal 0, right there, and right there, positive 2. And then here, when we write it as the product, that's going to be a positive 1/3 and positive 1. And you can see there's nothing changed here in our final solution, right? And yep, there you go. Looks good. So for the next one, now here we have this x cubed plus 1. I know many of my students, I kind of gave this away to them as far as for them to understand, but that's going to be the sum of 2 cubes. And if you don't remember the factored form for the sum of two cubes, I don't really feel it's that important for my students to have. Obviously, for those of them that are going on to further mathematics, I think it's important for them to have. But for the majority of my students that are not going to ever probably use this formula ever again, I just wanted them to be really familiar with it. And, you know, I do have this available, or I want to make that available for them on any kind of test and stuff. So, but the important thing, though, to understand when we're doing the sum or difference of two cubes is like this gives you your real solution, and then this gives you your complex solution, which I thought happened. Maybe that came up. Maybe I did. Oh, I did do this example. Okay. I thought I put that in the denominator. I guess not. Okay. So let's go ahead and factor that. So if I was going to factor that using this formula, it would look like this. X plus 1 times x squared plus 1 times x is just x plus 1. All over the factored form here, I could factor out a 2, right? So that's going to be x squared plus 2x plus 1. Okay, so that's going to be an x plus 1. Instead of writing this as x plus 1 squared, I'm going to write this as x plus 1 times x plus 1. Now, I'm going to skip a step here. I'm not going to write the division. I'm going to write it as the multiplication. So just be very careful when you're doing this. Take the denominator and put it in the numerator. So again, whenever you write that multiplication, when you change it, make sure you flip. And then this, you can see, is x minus 1. Oh, that's supposed to be a net. Oh, I messed up. My bad. Yeah, it's opposite sign. So that's plus, and then that's supposed to be the opposite sign. Ah, gotcha. Okay, so actually I didn't do this problem with my students. Or maybe I did a variation, I'm not sure. So this becomes x squared. Yeah, so that's minus there. X squared minus x plus 1. Okay, so now you can see that this whole quantity is going to be divided out with that whole quantity. Here, the x plus 1s divide out, right? Here, these x plus 1s divide out. Leave me just with the number 2. But it's the number 2 where x cannot equal, I think it was, hold on, I'm sorry. I just had to look at one of these fractions I was looking at, bothering me. Maybe I didn't do it. Sorry, I was just, okay. I don't know where I did one of those problems. So x cannot equal, let's see, x cannot equal plus or minus 1. And then, again, if you were to take this, the understanding we worked through these problems in our last unit, x squared minus x plus 1, if you set that equal to 0, you would get complex numbers. So therefore, we can confirm that those are not going to be any excluded values. So my only excluded values would be plus or minus 1. So again, the sum and difference of two cubes is just a factoring technique that we cover. Here's the difference of two cubes, in case you need to know it as well for your class. Sum and difference of two squares is, obviously a lot more common for students and used a lot more often. But now that we've kind of talked about that for polynomials, we talk about that sum and difference of two cubes that comes up, and just to be aware of it, and know how to apply it. And you can see in this case, it was very important. If you didn't know how to factor that using the sum and difference or the sum of two cubes, you wouldn't have got the right answer. All right. So now onto the last one is the simplifying complex fractions. So the reason why I love the complex fractions is because, one, you can't keep, change, flip this. You can, but it gets a lot more difficult, at least to understand the keep, change, flip kind of methodology. The other one is, when I taught Algebra 2, one thing I went over with the students is, you can always just apply the operation. Like if you get stuck in class, or on a test or on a quiz, like if you're doing this first problem, you're like, I don't know what to do. Well, then just add the numerator, add the denominator, and then you're going to have a fraction over a fraction, and then just multiply by the reciprocal, right? So, I actually showed the work over here. I get common denominators, and when I combine them, I get 7/12 divided by negative 1/12, multiply by the reciprocal, and I get an answer of negative 7. Now, that didn't take me very long, but you can see there's a lot of fraction operations, right? And so if that's your only option, fine. But the way that I like to think about this in this section is to kind of do something completely different than what we have done for the rest of class. I said, why do all of those fraction operations, okay? If you don't have to. Because my favorite fraction was 6 over 1, which is 6, right? My second favorite fraction is when you have like 6 over 2, because 2 divides into 6. Agreed? So therefore, that's actually doesn't, if you just simplify it, you don't have a fraction. So when you have a denominator that actually evenly divides into your numerator, that happens here too. But when you have another factor that divides into your numerator, you no longer have a fraction. So my goal here is then what am I going to do? What can I multiply everything by that 3 and 4, 4 and 3 all are going to divide into it? So basically what I want to do is find the LCD again. Well, the LCD of 3, 4, and 4 and 3 is going to be 12. So I'm going to multiply everything times 12, all right? Everything. So one thing you can do is you can just put everything in brackets and multiply by 12. Now again, when I multiply 12 times 1/3, 3 divides into 12 4 times. 4 divides into 12 3 times. 4 divides into 12 3 times, and 3 divides into 12 4 times. Therefore, that's leaving me with 7 over -1, which is -7, which is the exact same answer I got over there. All right. Over here, I decided not to do these two problems. I kind of changed them. And again, just following the same operation, multiply everything by 12, multiply everything by 12, multiply everything by 12. And the important thing is, what I want you to look at is every single problem. When I multiplied everything by the LCD, which in this case, everything was 12 every single time, notice how I only got one simple fraction, right? Look how many fractions are here. 1, 2, 3, 4, big one, 5. But when I multiply by the LCD, I only have one fraction, right? I just have one numerator and one denominator. That is the power of the multiplying by the LCD when you have a complex fraction. It means a fraction within fractions. Okay, so really all we're going to need to do is determine the least common denominator. We're going to multiply every single fraction by that least common denominator, and then we're just going to simplify. And in this case, though, I left off the complex. In this example, I'm going to leave off the complex or excluded values. Did I? Yeah, I did. Okay, so in this case, for my examples, I showed a little bit. I actually showed the distributing, okay? Because not always is something going to divide out here. Like here, the denominator is 1, right? And so my two denominators here is x plus 2, x minus 2. So therefore, my LCD is going to be the product of those two. When I multiply every single term here, now again, remember, x plus 2, x minus 2 is really also x squared minus 4. That's why when I multiply this times 2, I get 2 times x squared minus 4. Plus, here you can see the x plus 2 divide out, leaving me with a 1 times x minus 2, which is just x minus 2. The denominator here, I get 2 times that quantity, plus here the x minus 1's, x minus 2's divide out, leave me just with an x plus 2. And now it just comes into a simplifying and combining. And I didn't actually look to see if those actually get factored out, which, let's just see. I don't think that's 2x, 5 and 2. Oh, crap, that is factorable. Jeez. So let's see, that goes into 2x. I can't believe I didn't check that. So if I did this as a 2x, let's see, x minus 4. No, not 4, 2. Minus 2, and then this would have to be a -5, so that'd be a 2x plus 5. Let's just make sure that works. That becomes a -4x, that's 5x, so that does work. And then for this one, I'm figuring I'm probably gonna have to do, it's not gonna be 2x plus 5, so I'm assuming it's gonna be x minus 2. So therefore, this would have to be a 2x plus 3. And let's see if that works. It does. So therefore, my actual simplified result here turns out to be 2x plus 5 over 2x plus 3. So got to be very careful when you're doing these problems. Make sure you further simplify them. Again, I got a little bit lazy here and when I was creating all these, and I forgot to check to make sure that the x minus 2's divide out. So just a quick little thing, the excluded values are still going to be the same, but just make sure you kind of simplify them as far as the final step, right? Final step, simplify, and I forgot to do that. Oh, that's step number 3 anyways. All right, next one. Next one has 4 fractions. Fraction of numerator, and then again, look to factor this. You factor out that numerator, 2x plus 1 times x minus 2, and therefore now you have 3 different denominators, x minus 2, the 2x plus 1, and you got these. You identify the LCD, 2x plus 1 times x minus 2. Therefore, that's going to be that product. You multiply everything by there. You can show this distributive property, guys, but obviously if you're multiplying, if this is in the denominator and you're multiplying it by this, those are going to divide out, leaving you just with the number 2. Here, the 2x minus x minus 2's divide out. Here, the 2x plus 1's divide out. So that leaves me with x times 2x minus plus 1, and then x times x minus 2. When I go ahead and combine my like terms, I get 2 over 3x squared minus x. And then again, I did do excluded values over here. Oh, well, I didn't really mean to do excluded values. But you can see here the excluded values are the original denominators, which is 2 and negative 1/2. They also include, but again, now once you get to your simplified answer, you also see that the excluded values are going to now include, I factor out an x to be 0 and a positive 1/3. So the important thing about when you're doing complex fractions for excluded values, which I guess I might as well, I did do over here, is you're always going to look at the original excluded values, the values that make denominator 0 over here, and then once you get to your final answer to exclude the values. So actually, you know what? I guess let's just do excluded values. We're used to it, so it's good to go. All right, so I just got these 4 examples, and I think I gave myself more room. I did. Okay. So I'm actually going to show you also a different way now that I have a little more room to do this. So here, we're just going to find the product of their denominators, right? So you can see the product of the denominators is 2 and x minus 1. So I'm going to multiply everything times 2 times x minus 1. Now, in this case, I got a little more time. So I'm literally going to write out 2 times x minus 1 for everything. Okay, so now you can see the 2's divide out, the x minus 1's divide out, x minus 1's divide out, and the 2's divide out. So I like doing it this way better than really doing it that way as far as like a understanding portion. But you can see that obviously just writing it once, and kind of doing the work in your head makes things go by a little bit faster. So therefore, I'm going to be left with here a 3 times x minus 1. And then here, this is going to be a negative 2. All over, in this case, we're going to be left with a 2 plus a 3 times x minus 1. Now again, my terms are separated by addition and subtraction here, so you can't divide them out, right? But we can distribute them, which I could have done without showing it. I just wanted to kind of show that step. All right, so therefore I'm going to get a 3x minus 5 all over a 3x minus 1. So let's check our excluded values. We know that x cannot equal positive 1 because that makes that fraction 0. 2 does not make the denominator 0, right? That's just a number in the denominator. And then also we have 1/3, right? So if we were to set 3x minus 1 equal to 0, we would get x equals 1/3. So x equals 1/3 also makes the denominator equal to 0. So therefore, that's why it's excluded value. The next one here, we can see the LCD is just going to be a product of x times x plus 3. Now that I've already kind of shown it once, I'm not going to do it again because it's a lot of writing. So I'm just going to multiply everything times x plus 3. When I do that, you can see the x plus 3's divide out. That's just going to leave me with an x times x minus 2. I will show this at least one more step so you guys can see where I get that. Here, the x's divide out, so it's going to leave me with a negative 2 times x plus 3. Over here, the x plus 3's will divide out, leave me with an x times x plus 2. And then here, the x's divide out, leaving me with a positive 2 times x plus 3. Okay, so now it just comes in again to simplifying. So, x squared minus 2x. And you could save your step, right? I'm just doing it to show my work, so therefore people don't get confused or lost. Because, I remember when I was doing math, like that's where I lose. A lot of times I would get lost is when a teacher would skip steps. And again, for the sake of time, we have to skip steps, or not show everything every single time. Plus 2x plus 8. But I can definitely see how students, can still get confused. Now, that's not factorable, but I want to make sure that it's not going to be any irrational number. So what I could always do is check the discriminant. If you remember, the discriminant in the quadratic formula is b squared minus 4 times a times c. All right? And, yeah, okay, thank you. So if I did this discriminant, that's going to be under what's in the radical. Now, again, if that number is negative, that means you're going to have complex solutions if you were to use the quadratic formula. And the nice thing here is 4 times, or 2 squared is 4, times a, which is 1, times 8. And what you guys would see is that's going to give you a negative 16. So if you were to do the quadratic formula to solve for this, right, because this cannot be 0 in the denominator, what we would attain would be complex solutions. And again, there we know that we don't have any other restrictions there. We don't need to restrict complex numbers. So therefore, the only restrictions here are going to be negative 3 and 0. All right, moving on to the next two examples. In this one, again, we can see, oh, they have all three different denominators, right? But again, we can go ahead and factor this out. And hopefully, it's not always going to be the case, but it's probably a good wink, wink, that x plus 1 and x plus 2 are going to be the factors there, right? So therefore, you can see that my LCD is just going to be my product of my two denominators, right? Because this one shares both of them. So when I multiply everything times my LCD, let's see here, I'm going to get actually the factored form, x squared plus, let's see, that's going to be a 3x plus 2, if you multiply that out, times 1, plus, let's actually multiply this out. So the x plus 1's divide out, so that's going to leave me with a 2x plus 4, and I apologize if I make a mistake, but because this is usually where mistakes are going to happen, is when you start doing work in your head. The x plus 2's divide out, leave me with an x times x plus 1, so that's going to give me an x squared plus x, minus x plus 1's divide out, x plus 2's divide out, leave me with just a negative 1. All right, I can handle that. So now let's go ahead and combine our like terms here. So we have x squared is my only x squared. 3x and 2x, that's going to be plus a 5x. And then plus 6. Now the interesting thing here is, again, I recognize something that is, again, non-factorable. But I don't want to just say, oh, I'm not going to worry about these restrictions. What I'm going to want to do is go back to my original problem and say that x cannot equal negative 1 and negative 2. But now to actually go and solve these restrictions. So I'm going to set this equal because I don't want any number that's going to make this 0. Now, obviously, if they're imaginary numbers, then I don't need to worry about them. But I tested the discriminant in my head here, and I realized that it's going to work. It's going to give us an irrational number. 4 times a times negative 1. So in this case, we're going to have 1. That's going to be 5. Oops, what happened to my... Did the quadratic form not showing all the work? It's opposite of b, plus or minus, right? 5 over 2. So my restricted values is x cannot equal negative 1, negative 2, and x cannot equal negative 1 plus or minus the square root of 5 all over 2. So again, when you're identifying the excluded values, find the excluded values from the original problem and then from your simplified solution. And this is non-factorable, therefore I knew it wasn't going to divide out with anything else. All right, last example here. I'm going to want to rewrite that as a negative x squared plus x, factor out the negative to give me a x squared, or factor out a negative x, right? So if I factor out a negative x, that's going to leave me with a x minus 1. Okay, so now I have an x minus 1, and a negative. So my LCD in this case is going to be a negative x times x minus 1. So I'm going to multiply everything times all of those three. So here, my x's are going to divide out. But therefore, I'm going to have a negative x minus 1 times x minus 1. So let's see, that's going to be a negative x minus 1 times an x minus 1. Over here, my x minus 1s are going to divide out, so that's going to leave me with a negative x times a negative x. Over, everything divides out over here, leave me just with an x squared. All right, so this is because it's going to produce a perfect square trinomial. which is going to be a x squared minus 2x plus 1. Negative x times negative x is going to be a positive x. Now, all over x squared. Let's go ahead and distribute that. Negative x squared plus 2x minus 1 plus x all over x squared. And let's put it over here again. Let's combine our x. So therefore, we have negative x squared plus 3x minus 1 all over x squared. Nothing's going to like divide out. Don't need to factor it. So therefore, I know that x cannot equal 0 and x cannot equal 1. Those are my only two restrictions from there, from the original problem and then from the simplified version. And again, the x squareds cannot divide out, guys, because that is separated by addition. So really the main thing that I wanted students to work on is you can see how much factoring I just did. I did a ton of factoring, and I probably, hopefully, didn't make a mistake, but it'd be very common, and I wouldn't feel bad if I did, because I just did a lot of factoring. But that's the purpose that I want from this lesson, for you to gain some confidence in your factoring skills, and as well as to be looking ahead as far as looking for things to be factorable and looking for you to be able to identify the division property. But just don't divide things because they're the same. Make sure you can apply the division property correctly and also understand why we have excluded values. So that is how we ended basically the lesson, and then just basically want to see from students, what they understood from lesson, as well as what they kind of had trouble understanding. And then if you guys have any comments from there, I'd love to go and hear them, but I look forward to seeing you guys on the next video. Cheers.